So can you see it in full screen?
Yes. Yes,
Okay.
sir.
Yep. So, okay, so if we are ready, I think we can start whenever you want.
Okay, we can start, sir.
Yep.
I
Okay.
think we have enough participants.
Yep. Okay, no problem. Okay, so the talk that I was planning to give today is, as you can see from the title, it's not about rock or I don't know or deposit. It's rather about a single mineral that is rutile. And the point that I will try to make is that rutile is common mineral, and also it's a mineral that you can use in different applications, in different fields of sciences. So possibly at the end of this talk, you might have some, some ideas on how you can apply it to your own work. So rutile is tetragonal titanium dioxide. And among the titanium dioxide polymorphs is the most common in the Earth's crust. We can find it in metamorphic rocks, ranging in conditions from low metamorphic grade to granulate fascies. We can find it in igneous rocks, especially the felsic ones. And we can find it.
Sensei, sorry to interrupt.
Yes, sir.
Yeah.
We can hear your voice.
Yes. Can you see the images? Chandy? Chandy, can you hear me now?
So I can hear.
Okay, so I'll just proceed. Okay, so I was saying that we can see it in igneous rocks, in hydrothermal deposits, and also in mantle rocks.
Sensei, I'm sorry to interrupt.
Yeah.
But I get a message from Legion. So he's saying that your voice is still soft.
Okay. So how about the other people? Can you hear me? Or is it a problem of, you can hear me from here?
Yes, I can.
Okay, so it might be a problem of volume for some people. I try to talk close to my microphone, but that's probably not the issue, I guess.
No,
if you speak close to microphone, we can hear better, I think.
Is that right? Okay, okay. So I'll try to speak straight into the microphone. Yep, okay. So here you can see the difference between the different titanium oxide polymorphs. Apart from rutile, we have bruchite and anatase. So all of them are made of octahedra with a titanium cation at the center. And so the difference, sorry, the difference between different polymorphs is the arrangement of these octahedra. And so based on laboratory experiments and also on observations of natural rocks, we know that rutile is typically the high temperature and high pressure polymorph in comparison with the others. For example, in this figure, you can see experiments of conversion of anatase to rutile. You can see how rutile is stable at much higher temperature and P conditions. And similarly, when we look at natural rocks, we can find it in eclogites and granulites, that is high pressure and high temperature metamorphic rocks. However, there is ample evidence, and you will see it in this presentation, that rutile also forms at much milder, much lower PT conditions. Okay, so how do we distinguish the different polymorphs? we can use the optical properties. As you can see here in this little table, rutile is, for example, uniaxial positive, whereas anatase is uniaxial negative. Brookite is biaxial, and there's somewhat there's a difference in birefringence, and the absorption color is always a little bit brown and red and yellow, which somehow masks a little bit the birefringence. So it's not that easy to distinguish them in thin section, for example. So another way, another technique that is very effective is the Raman, laser Raman. This is a technique where we shine a laser onto the sample. We can do it on a thin section or even an unprepared sample. And that produces a spectrum with characteristic peaks, which can identify single minerals. And so here you see a comparison of a Raman spectrum of rutile, anatase, and brookite. You can see that the peaks are different, so we can effectively distinguish one from the other. And also another advantage is also that Raman is relatively widely available. One more technique that I will show you during the presentation is also the electron backscattering diffraction. It's also a rapid, high spatial definition and very accurate kind of technique. On the downside, there is that it's supposedly less widely available than Raman. It's a ACM-based technique where the samples are tilted at around 70 degrees, and when the electron beam interacts with these polished samples, we have diffraction of elements of the electron beam, and this diffraction produces a pattern or patterns called Kikuchi patterns, which can be collected by a special EBSD detector. And so with this technique, we can identify different mineral phases. For example, all the polymorphs of titanium dioxide can be quite effectively distinguished. We can also measure the 3D orientation of the grains, and that is important in microstructural studies. For example, here you can see an aggregate of rutile from a gold deposit in Western Australia. The top left is an electron image. The rutile is in the intermediate gray. Now the top right is the same grain mapped by EBSD. So the green color is the rutile, and pink is quartz intergrown with the rutile. At the bottom left, you can see the subgrain structure, where different subgrains are oriented in different ways. This is what is labeled the IPF coloring. Another thing that we can do is measure different misorientations or small variations in the orientation of the C-axis, and this can give us indications on deformation of rutile. Now, regarding the formation of rutile in metamorphic rocks, rutile can form at, let's say, medium or low metamorphic conditions by the stabilization of ilmenite. This is what you see at the top of this figure. And the reaction is schematically represented on the left. We have ilmenite reacting with silicates and water, producing rutile and chloride. Now that higher metamorphic conditions, we can also have biotite being destabilized to form rutile again. In metamafic rocks, one common reaction is the reaction between anorthite and quartz and ilmenite to produce garnet and rutile. This is pressure dependent and occurs at high pressure. And in metapolitic rocks, we can have other reactions, again, producing rutile and garnet at somewhat lower P conditions. Now, one important point is the incorporation of impurities in rutile, because many of the applications are based on the substitution of titanium by impurities. So here I'm listing some of the most common mechanism of incorporation of impurities. The first one is an isovalent substitution of titanium, which occurs in the 4+ oxidation state by other tetravalent cations. That could be zirconium, for example, or hafnium, vanadium 4+, silicon, and so on. So this is a simple one-to-one replacement reaction. We can also have coupled substitution of, for example, 2 titanium cations with 1 trivalent and 1 pentavalent ions. So the trivalent could be, for example, iron 3+ or chromium 3+, aluminium, vanadium 3+, and so on. And then adding a pentavalent cation, such as niobium 5+, ensures the charge balance. We have more couple substitutions. For example, we can have 3 atoms of titanium being replaced by 2 trivalent cations and 1 hexavalent cation. Or you can also have 3 titanium atoms being replaced by 1 divalent and 2 pentavalent cations. And so you can see that all these reactions have slightly different stoichiometries. And so if we measure the composition of rutile and we plot the concentration of some of these elements one against the other, we can try and understand the specific stoichiometry of this replacement, and we can have we can infer something about the oxidation states of cations that can be present in multiple oxidation states. This is, for example, the case of iron 2+ versus iron 3+, or perhaps manganese or vanadium, which can also occur in multiple oxidation states. Here, for example, you have a recent study where they looked at rutile associated with metasedimentary rocks and in the Athabasca basin of Canada, where we have uranium mineralization. And so what they did is exactly this. They analyzed rutile and they estimated the proportion of, for example, iron 2+ and iron 3+ in this specific rutile. So this is a method that I believe hasn't been used too much. It's a very simple, very traditional way of treating, for example, EPMA or laser ablation analysis. And for example, by comparing rocks, different rocks, or perhaps different, I don't know, mineralization stages, different alteration stages, I can possibly give indications on the evolution of the oxygen fugacity of the system. And another important application of rutile is the zirconium in rutile geothermometer. So we know that, and it's been known for some time, that the amount of zirconium, or let's say the partition of zirconium into rutile in the presence of zircon and quartz depends on temperature. And so you can calibrate geothermometers based on this. So for example, Zach et al. In 2004 produced a experiment, sorry, rather an empiric calibration of this geothermometer, essentially by taking samples of rocks with well-established temperature and analyzing rutile, zirconium in rutile. And so based on this data set, they were able to calibrate zirconium in rutile geothermometer. And after that, other people have conducted experiments where they essentially they equilibrated rutile with zircon and quartz and water saturated conditions in the lab. And so then at different temperature, they measure the amount of zirconium in rutile, and then they obtained an experimentally calibrated geothermometer. We also have even later calibration of the thermometer done by Tompkins et al. 2007, where they also considered the effect of pressure. Now, as you can see, if you consider crustal values of pressure, let's say the 10 kilobar curve, you can see that the thermometer of Watson et al. And Tompkins are very similar. So this is just to show you a few applications of this thermometer. It has been applied quite successfully in medium and high temperature rocks. And it, to a large extent, it relies on the fact that zirconium diffusion in rutile is quite slow. It's quite sluggish at any temperatures up to around 900 degrees. Above this temperature, the diffusivity is high enough that zirconium can exsolve and form exsolutions. And so in this example, you can see images of rutile from the Ivrea Verbano zone of the Western Alps, where rutile coexists with garnet and quartz. And so if you zoom in, you can see some of these tiny needles of zircon. So these are interpreted as exsolutions from the rutile as the rutile was cooling down, starting from very high temperatures. So in this study by Ewing, they analyzed rutile and they found a bimodal distribution of zirconium. The highest concentrations give temperatures of up to 1,000 degrees. And so this is interpreted to be the peak metamorphic temperature. And then they found a lower population of zirconium in rutile concentrations, which are interpreted to reflect reset at a lower temperature. Now, if we try to apply the same technique to lower temperature rocks, so far people have, the few people who have tried it, they found it a little bit more difficult to obtain good results. So this example is some analysis from gold, rutile associated with gold deposits in Western Australia, the Capricorn origin in red, and the Barberton Greenstone Belt in blue of South Africa, and Obuasi in Ghana in green. So for each one of these areas, we had independent estimates of equilibration temperature. And these are these pink and blue and green bands, the horizontal bands that you see in each one of these plots. Now, if you look at the spots, you see that the concentration of zirconium indicated on the x-axis is strongly variable, and that corresponds to strongly variable temperature estimates. Now, some of these temperature estimates overlap with the expected temperatures, but some of them are way higher, and some of them are unreasonably, impossibly high temperatures for these specific rocks. So the reason for this scattering, it's possibly the presence of small inclusions, such as these bright zirconium bearing inclusion you can see in this microscope SEM image. And we couldn't avoid them even with the PMA. Now, another important application of rutile is the chromium niobium provenance. Different studies have found that rutile from metamorphic rocks and rutile from metaphyletic rocks have different compositions. And so based on these comparisons, a specific diagram to distinguish rutile coming from metamorphic and metaphyletic rocks has been proposed. And we can apply this to the tritol rutile as an indicator of provenance of sediment. This is an example of such study from Chios Island in Greece. So in these two units represented here, you have again the chromium versus niobium concentrations of rutile. As you can see in both cases, the analysis plot across the dividing line, the one-to-one dividing line. And so one approach in this case is statistic, basically by simply counting the number of spots or the number of analyses plotting in one field versus the other one, which is the approach adopted in this case by Meinhold and other people, 2008. Okay, so the next application is uranium lead. As you can probably know, the application of uranium lead of rutile on and other minerals as well relies on a few conditions. One is that uranium content be high enough to be confidently detected and analyzed. And the other one is the lead so-called closure temperature. This is the temperature under which lead diffuses slowly in a specific mineral so that it can be trapped and the age can be preserved. So for rutile, we have broad indications on the closure temperature of lead, which can be somewhere around between 500 and 650 degrees. And in terms of uranium content, here you can see a plot of uranium content and also zirconium content of rutile from Western Australia. The dataset includes the tritol and metamorphic rutile. As you can see, there is overall a positive correlation between uranium and temperature. So this means that medium and high temperature rutile in general is easier to date. If you have low concentrations, let's say around 1 ppm or less than 1 ppm, that becomes quite difficult to analyze this uranium confidently. And also the amount of non-radiogenic lead present in the rutile might be much more relevant as a proportion to radiogenic lead. Okay, this is an example of uranium lead dating of rutile of quite high temperature. It comes from the Murari supersuite. These are granitoids. And so rutile in these rocks occurs in interstitial grains between feldspar and quartz. And as you can see at the bottom left, the analyses are quite concordant. So we could get a good age, which overlaps with the expected age of these granites. And the precision is quite high as well. Another example of uranium lead dating, this time from hydrothermal rutile. This is a little bit less usual because in many cases, hydrothermal and low temperature rutile is less concordant, strongly discordant, and it's harder to date. But in this specific case, the ages obtained are very good. So they obtained in these gold deposits from the North China Craton. They obtained an age of 122 million years, which then they compared with ages of magmatism in the area. And so their conclusion was that gold deposition and magmatism in the area are somewhat related. Now, the last point I would like to mention about this is that because there's a difference in zirconium and lead closure temperatures, this can cause a decoupling between the temperature and the age estimates. For example, if you consider crystallization of rutile at temperatures above the lead closure temperature, this is where lead can diffuse in rutile, but zirconium cannot. And then you assume that rutile cools down with time along this black arrow until it crosses the lead closure temperature. Now, until the rutile is above the lead closure temperature, the lead will diffuse and the age will be reset progressively. And so in this case, the age will be set at the moment where the rutile crosses the lead closure temperature. So what we will have is rather a cooling age rather than a crystallization age. But the zirconium in rutile temperature estimate will reflect the crystallization conditions. So there will be a decoupling between the two. Now, this is a problem in general, but it can also be used as an advantage when we want to do temperature time estimates. For example, in this case, in this study by Ewing et al. 2015, they looked at rutile in the Ivrea Verbano zone. You've already seen this data set before in the talk. In their reconstruction, rutile crystallized at high temperature at around 280 million years at around 1000 degrees. And then this was followed by a very long, very protracted cooling period until rutile crossed the lead closure temperature. And so the ages they found in rutile are around 180 million years, much younger than the expected crystallization age. So in the interpretation of these authors, this is due to a long cooling period. Okay, so in the next slides, I would like to focus a little bit on the applications of rutile to ore deposit studies and mineral exploration. But first, I need to introduce just a few points, a few ideas that then I will use later in the talk. So consider an ore deposit that forms by the ingress of a hot fluid, a mineralizing fluid that carries metals. This fluid comes in, it is in disequilibrium with the surrounding rocks, and it will react with the rocks. It will replace primary minerals with new alteration minerals, and it will deposit ore minerals. So this is what we call essentially the primary footprint of an ore deposit. The characteristics of these minerals being deposited will be a function of the fluid composition, the temperature, pH, and so on. And over the years, geologists have become quite good at identifying mineral paragenesis, textures, and distribution, so that now we can use this primary footprint as a vector towards the center of the system, a vector towards the mineralization. Now, this primary footprint can then be dispersed through erosion and through weathering to distal areas, even kilometers away from the ore deposit. This is what we call the secondary footprint. which derives from dispersion of the primary one. And so we can also study and target the secondary footprint, for example, by using indicator minerals. Now, to identify a good ideal indicator mineral, we will have to identify a mineral that, first of all, preserves chemical evidence of the primary mineralization processes. And then this mineral needs to be also weathering resistant and physically robust, so they can withstand a cycle of erosion and transport. So various minerals have been tested. That includes apatite or magnetite, rutile, zircon, titanite, and so on. Okay, so let's have a look at some examples of application of rutile in ore deposits. Here in this study, Scott analyzed rutile from porphyry deposits in New South Wales in Eastern Australia. So he analyzed rutile from high copper samples close to the center of the system and from other samples further away from the center of the system. And what he found is what you can see in these cross sections on the right, where you can see copper grades represented with different shades of gray. And the blue lines represent envelopes of vanadium content in rutile. So you can see that one line is labeled 4,000 ppm vanadium, and then further out you have 2,000 ppm vanadium and so on. So the main conclusion is that vanadium in rutile can be used as a tracer of mineralization in porphyry deposits and as a vector towards the center of the system. And this other example of study of rutile from porphyry deposits, this comes from El Teniente in Chile, which is one of the largest copper deposits in the world. So what they found, the authors Rabia et al. Found, is that rutile occurring in the porphyry itself, in the intrusion, has high concentrations of molybdenum. These are the black spots in the diagram. And also it crystallized at high temperature. This temperature was estimated based on the zirconium content. And rutile that is host in the surrounding mafic rocks that contain the mineralization are much lower in molybdenum. Now, this could be counterintuitive because the mineralized rocks have rutile with lower molybdenum. So the explanation is that rutile in the porphyries formed from a high temperature fluid that contained, it was oxidized, that contained high concentrations of molybdenum. Whereas rutile in the wall rocks crystallized during deposition during ore deposition, and so the most of the molybdenum will be taken from by the sulfides and by the ore minerals instead. So by using rutile, in this case, you can trace the evolution of fluids from high temperature to medium temperature and deposition of ore minerals. This is another example of a study of rutile from orogenic gold deposits in this specific case. What they did in this case is they analyzed rutile from different orogenic gold deposits in Canada. They distinguished ore and sub-ore, essentially mineralized samples, from unmineralized wall rock. And what they found is that the ore is especially enriched in tungsten, but also in tin and antimony. And so they could define a field in this triangular diagram of mineralized versus unmineralized rutile. Now, I would like to propose a slightly different approach. What most of these studies do is essentially analyzing rutile from the mineralized rocks and the immediate host rocks. Now, if you use this diagram, for example, and you plot some granite, some rutile from granite and rutile from a data set of metamorphic rocks, non-mineralized metamorphic rocks at different conditions, you see that a large proportion of these plot in the gold mineralized field, despite we know that these rocks are not gold mineralized. So there's a risk of false positives if you simply take this type of diagrams at face value without much care. If we plot gold deposits from the Barberton Greenstone Belt, from the Capricorn, Obuasi, plus some other gold deposits worldwide, all orogenic gold deposits. This is the same data set that I plotted previously. You can see that there's a large overlap, despite these are gold deposits. Now, if you do the same consideration with tin, then similar conclusions would be, you will find similar conclusions. And so it looks like, at least in our data set, antimony in orogenic gold deposits is more indicative of gold mineralization. So at least in the rocks that we looked at, it looks like antimony is higher in rutile from gold deposit compared to any other types of non-mineralized rocks. Now, of course, this is promising and encouraging, but it will need to be confirmed, perhaps by analyzing more orogenic gold deposits, different conditions, different age. And also another point that I personally would be curious about is what about different types of gold deposits? For example, porphyry copper gold deposits. Is rutile enriched in antimony in porphyry deposits as well? This is something that will have to be tested. And then just a final point that I would like to make is gold. So we are all looking for elements that can indicate the presence of gold in fluids. And can gold be incorporated in rutile? Because surely that would be the most direct indication of gold present in the presence of gold in hydrothermal fluids. Now, the simple answer is that so far, gold has not been convincingly detected in rutile. And there is also a problem of interferences, I have to say, both in EPMA and laser ablation. So that makes the issue a little bit more complicated. But certainly what we have detected is the presence of gold-bearing inclusions. This is what you see in this image from the Barberton Greenstone Belt. You can see rutile with different types of sulfide inclusions. So we analyze some of these rutiles with the laser ablation. And these are, on the left, you can see some of the results. These are, if you're not familiar, these are laser ablation spectra, where we're plotting the signal intensity as counts per second, CPS, versus the analysis time as seconds. So the analysis starts on the left and finishes on the right at around 70 seconds. You can see background collection in the first around 15 seconds, and then the laser starts ablating the sample. So you can see the signals going up. The blue line at the top is titanium. It's quite flat, as you can see. But the gold, for example, in yellow towards the bottom of the diagram is quite up and down, it's quite spiky. And you can see that gold goes up and down together with chalcophile elements, and also together with sulfur. So that suggests that this gold is present not in the rutile itself, but is rather present in sulfide inclusions. But nonetheless, this type of finding can supposedly also be used in terms of exploration for gold deposits. Just a few final messages. So rutile is a common mineral. It occurs in a large range of crustal and mantle rocks. It is useful because it can be used to gather information on a series of aspects of rocks. So we can infer real geological information in terms of provenance, temperature, oxidation state, age, and so on. And more specifically on ore deposit studies, I believe that the detrital rutile has a potential application in large-scale campaign style studies of large areas. So one point is the one that I shown. So the antimony in the exploration for orogenic gold deposits, but other types of deposit can also be targeted. So let's say that this is a relatively new and expanding field where new findings are being made at present. And just to conclude, I will just leave you with some of the references that I used to make this presentation. And also I should mention that much of the work done on rutile was done at Curtin University in Western Australia in the last years, together with Steve Reddy, Diana Plavza, and Hugo Olirook, plus other people. And yes, so this is what I had to say. Thanks for listening.
Thank you very much, Professor Agangi. So now I'd like